be delivered in sequencing. But unreliable network, anything can happen, like an IP. Okay, Internet Protocol is an unreliable network. So where there is no guarantee that something will get lost, something will not be delivered, right? It will get delayed, right? Such scenario, this credit scheme works well for flow control. So as you can see that just as you remember the sliding window protocol, in the similar manner as the bank grants you some credit for your credit card, and once you spend the money on your credit card, the amount, the limit gets reduced, right? And once you pay the bill, you once again get the full limit, right? So the same way, once this is the initial sequence number from where it is started, the initial sequence number, the sequence number are assigned that first of all octet, that the size of a segment is determined. That is how what will be the size of a segment, suppose 200 octets. So it is completely a discretion of the TCP to decide the size of a segment. Okay, and once so the initial sequence number, and this is the last octet acknowledged, right? And this is what the last octet transmitted. So what this is about the sender side. So sender makes a record of all the segments which were transmitted and acknowledge those which were transmitted but not yet acknowledged. So window shrinks from trailing edge as segments are sent. So this will shrink, right? And it will expand from leading edge as the credits are received. So as long as you get the acknowledgement, or as not the acknowledgement, as the new credit is allocated, right? As I told you earlier in the previous class, that the receiver determines that how much buffer space is going to be free, and based on that it allocates or it increases the credit limit of the sender, right? So this window extends. Similarly here at the receiver side, this is what it has acknowledged. This is the last octet received, what it has acknowledged. So window shrinks from trailing edge as the segments are received. Window expands from leading edge as credits are sent. So more credits are sent means it gets enlarged, right? So just this is about the credit scheme. Now we will talk about the connection establishment part. So this credit scheme was related to your flow control. Now we will talk about, like in a reliable sequencing network, how the connection establishment took place. So why this connection establishment is required? So we need connection establishment and termination procedures to allow each end to know the other exists. Right? There are two TCP entities. They want to communicate. How will they know about each other? So to know about each other, or to open a connection with each other, they need to follow some steps, right? They need to go through some negotiation kind of thing, that if they are opening a connection, that what are the optional parameters they will select. Okay, so that includes that what will be the maximum segment size, what will be the maximum window size, what will be the quality of service they can agree on, right? So buffer space. So all those things they need to first settle down before finalizing the connection in an open, before putting the connection in the established state, right? So so first of all they exchange some kind of a synchronization messages to know each other, whether the other TCP entity is free to open a connection or not. And once they are agree, then they finalize the optional parameters. They negotiate on the optional parameters. As I said, that the maximum segment size, what will be the window size. Okay, all those things they negotiate, and then to provide the quality of service They triggers allocation of transport entity resources, right? So how does it work? So this is about a connection state diagram. You can see here that there are two sides. This is one side, this is one side. Okay. So you can see that these ends are event and then action. Okay. So any TCP entity which is actively open means it is ready to open ready for a connection establishment, right? And this is passively open means it is not yet ready, but it is hearing it is in the listen state. It can hear any request from the other party, and if it finds okay, it can connect, right? So it is passively open. So in this passive open means it is listening to the request, right? So initially the connections are closed, and this TCP entity is actively open means it is ready to open a connection, right? But the other party is passively open, so they can listen, but they cannot respond. They cannot start a connection. They are not in a mood to start a connection, but they are ready to open up if some request comes, right? So this party sends a SYN. Okay, SYN stands for synchronization frame. Okay, this synchronization frame serves two purposes. First of all, you can consider it as a request to open up a connection. Secondly, it also serves as an acknowledgement of a request. Okay, so this party sends a SYN. Okay, this side, which is actively open, this sends a SYN, and once this party receives it, which is in the listen state, once it receives SYN, and if it is ready to open a connection, okay, it can, if this party also replies back with a SYN, okay, if this party also replies back with a SYN frame, okay, synchronization frame. So once both the parties exchange a SYN, that means a connection is put in the established state, right? I hope it is clear that the connection will be put in a established state once both the party exchanges the SYN. Okay, and then following that, the data transfer will start. So this is about a connection state diagram, that how the connection is put in the established state. Okay, similarly, how a connection is being closed. So I told you that there are two ways to terminate a connection, right? One can be an abrupt termination of the connection that may lead to the loss of the data which is in the transit. Okay, so the data which is in transit, that will be lost in case of an abrupt termination, but there is a gradual termination. There is a procedure of gradual termination that leads to the termination only when the data in transit is recovered successfully, right? So there is no loss of data. So here you see that this is about the connection establishment part. The upper part of this diagram shows the state diagram for the connection establishment, and the lower part says about the procedure for connection close. Okay, connection termination. So you can see that this party, okay, any party can send a connection termination request, right? So as I told you that this can be a gradual termination or this can be an abrupt termination. In case of an abrupt termination, the party will send a thing and put the connection in a closed state, right? But if you see, if it is a gradual termination, how does it work, right? So suppose any party, suppose this side, okay, this TCP entity wants to close a connection. Okay, so it sends a FIN. FIN stands for finish. Okay, so FIN command is for finish. So it sends a FIN and it puts the connection in a FIN bait state. Just like SYN, when both the party exchanges SYN, the connection is put in the establishment state. Similarly, when both the parties get a FIN, exchanges FIN, the connection is put in a closed state, right? So once this party sends a fin to the other side and put the connection in a fin wait state. This party receives the, basically there are two things. One is the TCP entity, one is the TCP user, right? So this, because this TCP entity is working on some TCP user, right? So this TCP entity, when it gets a instruction from its TCP user that it wants to close the connection, it sends a fin and put the connection in a fin wait state. So upon receiving a fin from the other side, this side, okay, it informs on receiving fin, it informs its TCP user that the other side has send a fin and wants to close the connection, right? So it puts the connection in a close wait state and informs its TCP user that the connection has been put in a close wait state upon receiving a fin from the other side. And once this TCP user at this side gives the instruction to the TCP entity, because and the moment the data in the transit is recovered, right, this connection upon receiving the instruction from the TCP user, this connection will be it will send a fin and will put the connection in a closed state, right? So upon receiving fin from this side, this side will also put the connection in a closed state. Okay, so are you following that? This side will initiate a close request by sending a fin, and will put this side in a fin wait state for connection close. So, and this side upon receiving a fin, it put the connection in a closed wait state, inform its TCP user that a fin is received from the other side, it wants to close the connection. So once the TCP user instructed TCP entity to send a fin, and once it sends a fin, it puts the connection from a closed wait state to the closed state and sends it. So once it receives the fin this side, it put the connection in a closed state. So this is how the connection is being closed or terminated. So this is just like how the connection establishment happen. That this is system A, this is system B, right? So both of them, a connection is closed. This shows the previous connection got closed. Now they want to open a connection. This side B wants to open a connection with A. So system B is actively open. Okay, it is interested in opening a connection, while this side, which is passively open, it can only listen. And if it wants, it can open a connection, right? So it sends a SYN, right, to this side, and if this side agrees or this side is interested, it can replies back with a SYN and putting the connection in the established state, right? So this is the case when one side is passively open, another side is actively open. Now you see that when both the sides are actively open, both the sides wants to receive wants to open a connection aggressively, both can send a SYN to each other and put the connection in established state, right? So if a TCP entity receives a SYN from the other TCP entity, it puts the connection in a established state. Similarly for the fin also, right? Fin also, there is as I said that when both the parties receive the fin from each other, the connection is being terminated, right? So here also the connection will get terminated. So first of all, this synchronization, right? Jaruri nahi hai ki this SYN will be exchanged immediately. Okay, ऐसा भी हो सकता है that this party has initiated a SYN to the other party, but there is no response. Okay, though this is in the listen state, so it has sent a SYN to this, but there is no response from this side, right? So, and this will get timed out. The system B will get timed out and will once again send a SYN to open up a connection, right? And then it may get a reply from the other side to put the connection in a established state. So as I said that the connection termination is a process that either or both sides by mutual agreement. So it can be a graceful or an abrupt termination. So if graceful, as I told you that it should send fin to other end requesting termination, place connection in a fin wait state. The side which is requesting the termination will send fin to the other end requesting termination, place the connection in a fin wait state, and when fin received from other side, it informs its user and close the connection. And other side, when receives fin from this side, when it receives from fin from the other side, it informs TCP user, right, and place the connection in a closed wait state. When TS user issues close primitive, when the TS user will issue a close primitive, it will send a fin to the other side and will put the connection in a closed state. Right? So this is how the connection termination works. So now we will talk about the unreliable network service. So you know that in an unreliable network, as I said, that there is no guarantee of anything. Like an IP internet is an example of that. So here the segments may get lost. Segments may arrive out of order. Both the issues are very, very critical when you think in the in view of a TCP, right, which is known for its reliability and it provides an end-to-end services, right, from process to process delivery with flow control, error control, everything. Even the lower layer leaves it to the TCP for sequencing of, like, if you remember the IP, the segment, this datagrams arrive out of sequence at the receiving end. But this is TCP which takes care of these things, that it provides the sequencing, okay, sequencing of the fragments. So here, when we talk about an unreliable network, these things are very, very critical. That the loss of segments and then arriving of them with in different orders. Then there are duplicate segments. So these issues are very, very important when we deal with the unreliable network service. So there are many examples, like you can remember this 802.3 unacknowledged connectionless LLC or IP internet. These two you have studied, right? A datagram style and this frame relay. So what are the issues basically? The issues are order delivery. What should be the retransmission strategy? Duplicate detection, flow control, connection establishment and termination, and crash recovery. Order delivery should be there. So as you know, order delivery, that though the segments may arrive out of order, okay. So what could be done? First of all, what we can do, we can assign a sequence number to each segment, okay. So how the sequencing is done, as I told you that in the example, in a credit scheme example, that how the sequencing is done, that TCP numbers each octet sequentially. That first of all, as I said, that the two parties are there. Based on their negotiation, they decide the size of a segment, right? How many octets will be there in a segment, and based on that, the TCP creates segments and it numbers each segment sequentially. Like the first segment, starting from the first octet, will be given a sequence number, the first sequence number, right? And then later on, based on the size of that, like you remember, it was 1001, then the size was 200 octets, so it was 201, right? So like you see that if the size is of 200 octets, if it starts with the sequence number 1, the next sequence number of the segment will be 201, then 401, then 601, like that. Or if you start with 1001, right, it will be 1201, 1401, like that. So segments are numbered by the first octet number in the segment. So what should be the retransmission strategy? Yesterday also we discussed a bit that retransmission strategy, when the sender should retransmit the frames. What should be that retransmission time? How will you select a retransmission time? Because the network conditions may change very abruptly. So how will you decide on the retransmission time? So as I said that why the segment retransmission is needed? Because the segment damage is in transit, they are failed to deliver at the destination, or segments fail to arrive, they get delayed, they get lost, right? So and the sender gets timed out. So first of all, the sender is unable, sender is not knowing about this failure. So receiver must acknowledge successful receipt. That whatever the segments are successfully received, they should acknowledge those. Cumulative acknowledgement can be used for efficiency. So sender times out and waiting for acknowledgement, so it will retransmit it. So timer value, what should be the timeout value? We discussed that if you are using a static value of a timer, what could be the consequences? Suppose based on the understanding of the network behavior, like you decided that from Mesra to Ranchi it takes 45 minutes by a four-wheeler, right? But कभी जाम हो सकता है, कभी नहीं भी हो सकता है. You may reach early also, you may reach it will get delayed also. So if you use a fixed time value, okay, based on the understanding of the network behavior, so fixed time value means it is not adaptable to the network conditions, which may change abruptly. Okay, if you choose a small value of this retransmission timer value is small, right? The sender will time out very fast and will lead to retransmission of segments, which will further congest the network, right? And if you took too large value, that will make like too large value means like as I said, there is no traffic. Suppose when you have to catch a train or a flight, you start early so that you can reach in time. But sometimes when there is no traffic, you reach much before time, right? Then you feel that I could have started late. So the same thing, that if you took a very large value of this retransmission timer value, then the protocol will become sluggish, right? So it should be always, generally we consider a bit higher than the round trip time, right? So this is what the disadvantages of using a fixed timer value. So we can have an adaptive scheme which is purely based on the current network conditions. So but there is an issue with that also, because how will you say that suppose how do we judge that what is the network condition? See, how do we learn anything? From our previous experiences, from our past experiences. So similarly here also in a network, how do you know about the network conditions? Suppose you send a segment from this end, okay, to the other end of the network, and you wait how long it takes for a segment to be acknowledged. Okay, so if you get a positive acknowledgement during a certain period of time, you assume that this amount of time is required for a segment to be acknowledged, right? delivery and acknowledgement, to and fro movement from the sender. So, but what are the issues with that? So if we immediately use a previously received segment's behavior as an input, right? The time that a previously sent segment has taken as an input. There are many other things that should come into account. That as you know that there is a cumulative acknowledgement. So the receivers may not send the acknowledgement immediately. They may hold an acknowledgement for a longer period of time. As I said, that the receiver holds the acknowledgement for a cumulative, to send a cumulative acknowledgement. So the segment which you have sent and is being acknowledged from the other end will not depict the true behavior of the network conditions. Because if the receiver has holded the acknowledgement, it will send it late. It may send the acknowledgement late. So it will not depict the true behavior or the true conditions of the network. Are you following? So acknowledgement may not come immediately. Then you cannot distinguish between acknowledgement of original segment and the retransmitted segment. Why you cannot distinguish? Because you just see, you send a segment, from the sender sends a segment to the other side. The acknowledgement is holded by the receiver, right? But or the acknowledgement is sent by the receiver, it gets delayed in the network because it is an unreliable network. So the sender gets timed out, right? Sender gets timed out, it retransmits the segment again. And because of that, what will happen? It will receive another acknowledgement, right? So, it will not understand whether this acknowledgement is of the original segment or the retransmitted segment, right? So these are some issues like duplicate detection and other things. Duplicate segments will come. So conditions in the network may change suddenly, right? So duplicate detection, like if you can see here, I have just drawn it, that this sequence number 1, the first segment is transmitted from this side to this side. Okay. Then following that, it transmitted another segment starting from sequence number 201. Right. But it gets timed out. It gets timed out, the sender, but no acknowledgement came. The sender gets timed out. Okay. It resends segment sequence number 1, sequence number 201, right? And then because this acknowledgement from here, this acknowledgement got delayed and appear over here. Okay. So, and this acknowledgement also comes. So which acknowledgement belongs to which? So there will be duplicate 2 acknowledgement the sender is receiving. Okay, for the same sequence, for the same segments. Following it, because this acknowledgement got delayed in the network and it appears here, right? So this is also an acknowledgement which is expected from this side. So multiple acknowledgements are received by the sender for the same segments, right? So this issues, so duplicate, so which one should be taken as a valid one, which one should be discarded, so which one depicts the actual behavior of the network condition, right? You can see there are 2 acknowledgements received. So which one should be considered as the correct, which exhibit the correct characteristic of the network? right? So if you take this as an original one, then it takes a lot of time to reach, right? So it will, if it sets the timer value based on this, that may not be correct. Or if it is an acknowledgement of this, then also then it is correct, right? So it depends. So which sample should be taken, which depicts the clear picture of the network, right? It's very difficult. So which timer value should be chosen, so that, because as I told you, there are two components of congestion. One is a window that is assigned by the receiver to the sender, that how many segments a sender is allowed to send. Another factor is the timer. Okay, that because if you choose an improper value of timer, that may lead to multiple retransmissions. Okay, multiple retransmissions. So now duplicate detection. Are you following? What's your name? Hassan, are you following this?
Yes, sir.
So in which case our duplicates will be there.
So when the receiver holds the acknowledgement and maybe delays it, and the transmitter is retransmitting.
So there are duplicates for both SYN also, for any segments also, right? So how to deal with this situation? As you have understood that these two segments are sent, then it is retransmitted, it sends again. Okay, so suppose this acknowledgement which should come, it failed to reach, and it sends it again. Okay, so which acknowledgement? So it receives multiple acknowledgement if it gets delayed in the network. So which one should be taken? Now there are two cases for this duplicate detection. If it is coming prior to the close of a connection, or if it is coming after the close of a connection, right? Just see the example. This is what prior to the close of a connection. What is the meaning of prior to the close of a connection? Means still the two parties are engaged in exchanging of data, right? So this is transport entity A, this is transport entity B. So it transmits sequence number 1, okay, sequence number 201, 401, okay, but this sequence number 1 frame got delayed in the network, right? So there is no acknowledgement. Okay, there is no acknowledgement. So basically there is a timer for each segment now. So for the sender times out and retransmit the sequence number 1. Okay, and the receiver acknowledges all the frames up to 601. Are you following? In the beginning, it transmits sequence number 1, 201, 401. So one failed to reach at the destination, it got delayed in the network. It got stuck in the network, it failed to reach at the destination. So, and by the time the sender times out, it sends sequence number 1, sequence number 201, and it receives an acknowledgement. It receives an acknowledgement AN601. What does it mean? Anyone in the class? What does it mean, AN601?
Sir, all the segments before 601 are received.
So all the segments up to 401 are received. It demanding a new segment starting from 601. Yes. Right? And this is what the window this says the credit. Okay, so this SN201 which it transmitted, the sender has transmitted now, is a duplicate at the receiving end, right? It's a duplicate. So you can see that when the data is in exchange process, data is exchanging, the two parties are exchanging the data. So the connection is not closed, right? The connection is not closed. It is exchange is in progress. So here this is a duplicate, right? So then this is also a duplicate. No, this is not a duplicate. This acknowledgement is also a duplicate, right? Because by the time it reaches over here, it demands. So it's a duplicate. You can see. Then it sends 801, and then it demands 801 again, right? So this is what there will be duplicates, and this you consider here that this sequence number 14, it reaches 1401 because it has given a 600 credit size. So see what should be the size of a sequence number is also a big thing, that the sequence number space should not be repeated, right, in a segment's lifetime. Otherwise what will happen, you see the scenario here, that once this sequence number 1401 reaches over here and the sequence number space get exhausted. So what you have to do, you have to once again start from the sequence number 1, right? So once the sender started sequence number 1, and before this reaches at the destination, this delayed sequence number 1 appears over here, right? So the receiver assumes that this one is original. It may consider it as an original one and discard the original one, right? So this delayed segment with sequence number 1 can be considered as an original one, while the original one can be discarded by the receiver, assuming it as a duplicate, right? Is this process clear? So that what it can do,
Yes.
that if a duplicate appears prior to the close of a connection. Now there is another scenario, right? I will come to that. Yeah, you see here that after the connection is closed, right? So suppose one connection is closed. The connection is closed between the two parties. Then they want to open up a connection. So this party sends a SYN. The other party also sends a SYN. The connection is put in the established state. Then this party starts sending the segments starting with sequence number 1201. And before it transmits this sequence number 401, this segment from a previous connection, okay, from a previous connection, because the connection was closed, from a previous connection appears over here, right? So the receiver considered it as a valid segment and discard the original one. So this is what the case of duplicate appearing after the close of a connection, right? Followed both the things, that the duplicate arriving prior to the close of a connection and duplicates arriving out after the close of a connection, right? So what should be the way to deal with such eventualities, right? So if acknowledgement is lost, segments get duplicated and retransmitted. So receiver must recognize duplicates. If duplicate received prior to closing of connection, receiver assumes acknowledgement is lost and acts are duplicated. Are you following? Okay, that if the duplicate appears prior to the close of a connection like this, right? The receiver should assume that the acknowledgement is lost, and that is the reason that the sender has sent it and it's a duplicate, right? Sender must not get confused with multiple acknowledgements, right? And receiver must be able to detect the duplicates. Okay. And another factor that comes out to be that a sequence number space should be large enough to not cycle within maximum lifetime of a segment. Because you have seen that if the sequence number could have been large, 1401 से बड़ा होता, 1601, 1801 अगर sequence आ रहा होता, then this issue could not have happened. Okay, तो फिर ये issue होता ही नहीं that this sequence number 1 appears here and being treated as an original one. So this would not have happened if the sequence number had been large enough. So following. So now the next issue is the flow control. So as we have seen that the credit allocation is a quite robust with unreliable networks also. It can acknowledge data and grant credit, or just one or another. It can acknowledge all the segments without giving further credit. So if any acknowledgement is lost, okay, so once you get the new acknowledgement, like in this case, if suppose this acknowledgement is lost, AN601 is lost, right? So the moment AN801 is coming, so that means it has acknowledged all the previously received segments, right? So even if any acknowledgement is lost, the next acknowledgement will acknowledge all the previously received segments, right? So the credit scheme is very, very robust, but there is a problem of deadlock. There can be a deadlock condition can occur, right? In a between the two transport entities, a deadlock condition may occur in a following scenario. In this scenario, like suppose one party, there are two parties, A and B, right? So suppose B doesn't want to give any acknowledgement to A. Okay. So what it does, it sends an acknowledgement I that says all the previously received segments up to I-1 are acknowledged, and it make the window to 0. Okay. So in between the window is made to 0. So that means it has closed the window. Right? No credit is assigned to the sender. So once it transmits this ANI with W0, right? It says that it has acknowledged all the previously received segments with the new credit is 0. So it has closed the window, right? And so sender will be under the impression that no credit, I cannot transmit further. But at the same time, after some time, B realizes that it should open a connection. It should give some credit to A. So it sends again, just following this acknowledgement, it sends another acknowledgement with AN equal to I and W equal to J. Right? So that means what? It is acknowledging all the previously received segment, and it is assigning a credit of J octets to reopen. But this acknowledgement failed to reach at the destination, failed to reach to the sender. Now what is the scenario? B is thinking that it has given a credit to A, and A is thinking that it has no credit to send any segment. Right? So this situation will be a deadlock situation between the two. Right? No party will send anything because B is sending, so no exchange of frames will be there because A is under the impression that it has no credit to send, while B is under the impression that it has assigned the credit to A So it will send. So a deadlock will occur between the two parties. So how a deadlock can be broken, right? So sender thinks that the window is closed, receiver thinks it open. So what is the solution? Solution is to use a timer, persistence timer. Okay, so this timer is basically get repressed every time with the movement of the frames, with the movement of the segments. Okay, when the two parties exchange the segment, this persistent timer get refreshed with the passage of this segments, right? And if there is no passage of, there is no passing of segments, the persistent timer will expire. Okay. So if timer expires, what it does, it sends something. So it could be a retransmission of the previous segment, so that a deadlock is broken between the two TCP entities, right? So okay, then this connection establishment, these things we will do in the next class, right? Any doubt? Okay, thank you.